Hi, welcome to week 3 of the NPTEL course on Haskell. We will continue our discussion on lists. Just to recall what we had covered in the previous lecture, uh, in Haskell, lists are the data structure that one uses to describe a collection of values. For instance, 1, 2, 3, 1 is a list of ints, true, false, true is a list of bools, and so on and so forth. Just to recall, all elements of a list must be of uniform type. You cannot mix types, and lists with value of type t has type list t. You pronounce it as list t and you will write it as t within square brackets. Okay, this is just a quick recap of what we did last week. So 1, 2, 3, 1 is a list of type list int, true, false, true is a list of type list bool, and so on and so forth. You can also nest lists. So you can have a list consisting of the list 32, the empty list, and the list 777. This is of type list of int. So to build a list, you start with the empty list, which is denoted by just the square bracket without anything written in between, the empty square bracket, if you will, and then you use the colon operator to put an element before an existing list. So you put 3 before the empty list, that will give you a list consisting of just the element 3, and you put 2 before the list 3, this is equal to this, and this is nothing but the list 2 comma 3, and you can put 1 before the list formed by putting 2 before the list formed by putting 3 before the empty list, which is nothing but 1 preceding 2, 3, which is nothing but 1, 2, 3. And you can put 0 before that, and that will be the list 0, 1, 2, 3. Yeah, so you can build all Haskell lists this way by starting with the empty list. Since you build a list using colon, you can also take apart a list based on its colons, based on its structure. But just before that, notice that colon is right associative. So I can write 1 colon 2 colon 3 colon empty list without any parenthesis at all. And you decompose list mostly using pattern matching. And here is an example. Yes, so you use, here is an example where I define the length function on lists. Length of empty list is 0, that is this class, and length of the list x colon xs is 1 plus length of xs. Yeah, length of the list x colon xs is 1 plus my length of xs. So this is the basic pattern matching in Haskell, and this also illustrates how you do recursive definitions on lists. The definition of any function on the argument x colon xs is defined in terms of the same function on xs. And then we looked at a bunch of functions. Here was one function we looked at, add at end. You wanted to add an element at the end of a list. If you want to add x to the end of the empty list, you just get the list consisting of just the singleton element, you get the singleton list consisting of just the element x. If you want to add x to the end of y followed by y's, you add x to the end of y's, and then you put back y in front of it. Okay. So unlike with arrays where you can just go to any index of the array and add an element and modify the element there, in lists, of course, lists don't have any restriction on the length. You can have any number of elements in a list. So you can add elements to a list, extra elements to a list. But if you want to add something in the middle or something at the very end, you have to traverse the whole list from the beginning to that point where you want to insert it. Okay, and if you can add one element to the end of a list, you can also add a bunch of elements to the end of a list, or in other words, you can add a whole list L2 at the end of L1. And there are two ways of programming it, you can do structural recursion on the second argument, but if you do that, you will have to call the add at end function during every recursive call. Okay, and that is costly because add at end has to traverse the whole list. So you start with the second, you take the first element of the second list, add it to the end of the first list. That will take time proportional to the length of the first list. And then you take the next element of the second list and add it to the end. That will take once again whatever length of the list time. So on and so forth, and in general you will have to spend time proportional to length of L1 times length of L2. And a smarter way to do this would be to do structural recursion on the first argument, right? And this is better because all you need to do is, if I want to attach x colon xs to the front of L2, I attach xs to the front of L2 and then I put back x in front of it. Okay, and we saw this, and this version of attach is the built-in function plus plus. Okay, when I refer to it as a function, I should put it within parenthesis, but when I use it as an operator, I will use plus plus without parenthesis. So I can say 1, 2, 3 plus plus 4, 5, 6, and that will give me 1, 2, 3, 4, 5, 6. Okay, so we finally also had a function that extracted the value at a given index where the indices start from 0. So if the index itself is less than 0, then you say that it's an error, you say negative index. If the list is empty, then there is no index in the list at all. So even if your index is 0, that's a too large an index for your list. So you will say index too large. Otherwise, if your index is 0, you return the first element. Once you have gone past the first two lines of the definition, you know for a fact that n is greater than or equal to 0 and that the list is non-empty. So your number will be 0 or more and your list will be of the form x colon xs. So if you want to extract the position and value at position 0, it's just x. The value at position n is just the value at position n minus 1 of the tail, which is xs. Okay, so we saw all this last week. And finally, we saw a nice program to reverse the elements in a list. If you want to reverse a list, you reverse the list into a accumulator, or rather, so reverse into this is what you are computing. Rev into is actually has this behavior. So therefore, if I do rev into empty list L, then I will get nothing but reverse of L plus plus empty list, which is nothing but reverse of L. Okay, so rather than just computing reverse, you compute actually a more complex function, but the more complex function has a direct definition without referring to reverse. So rev into, if you want to reverse the empty list into A, an accumulator A, it is nothing at all, it is just the accumulator. Reversing x colon xs before A amounts to putting x before A and then reversing xs before that, and that's what the code says here. And this automatically reverses the list as we discussed last week. Okay, so this was a quick recap of the material on lists that we covered last week. Today we will continue with more discussion on lists. Okay, so specifically we will look at built-in functions on lists, and there are a lot of built-in functions in Haskell. There is a extremely rich support for lists, and there is some very extremely convenient list notation that Haskell allows you to use. We will look at all this in this session, and in the demo session we will actually run it on GHCI. Okay, let's begin this lecture. Here are a bunch of built-in functions on lists. Head on x colon xs will give you x. So, if your list is this, head will extract this part and tail will extract this whole part. Yeah, tail x colon x's will give you x's. Importantly, head and tail are undefined on empty list. So, one has to be a little careful about using head and tail. In fact, GHCA will automatically give you various warnings if you use head and tail. So, you either need to figure out how to switch off those warnings, or you need to actually fix the warnings by replacing the use of head and tail with some other means. In fact, in the previous lecture we showed how you can actually avoid head and tail by using some kind of pattern matching local definitions. Okay, anyway, so here is length. Length of the empty list is 0, length of x colon x's is 1 plus length of x's. Here is summing all the elements in a list, but for this the elements of the list have to be some numeric type. You can't sum all elements in a list of characters or in a list of Boolean values. Okay, so sum of empty list is 0, sum of x colon x's is x plus sum of x's, right. So, you could write it in some kind of mathematical notation as this. Okay, so here are some more functions. Init. So, we saw head and tail. This is head and that is tail. This is the most natural way in which lists are decomposed in Haskell, but you can also try to decompose it as the last element, which is called last, and all elements other than the last element, which is called init. Okay. So, notice head and last are elements of type A, whereas tail head L, I must say, head L and last L are elements of type A, whereas tail L and init L are lists of type list A, right. So, for instance, I might have a singleton list 5, its head is 5, tail is empty list, init is empty list, last is 5 for this list. Okay. So, that is just an example, but of course, this is just an extreme case. And if I have the empty list, of course, all these functions are undefined. Init, last, head, tail, all of these are undefined on the empty list. Okay. So, init returns all elements except for the last element. Last returns the last element of a list, and both these are undefined for the empty list, and actually you can define these two functions. This is the definition given in the Haskell standard library. Init of the singleton list x is empty list, init of x colon x's is x followed by init of x's. So, if I have to find out the initial portion of a list, then what I will actually do is I will go till the end. At this point, I will replace this by empty list, and I will have to put back all these elements again. So, remember that any list is of this form, x1 followed by x2 followed by x3. Now, I need to go all the way here and replace this by just the empty list, but then I have to put back all those elements again. I strip off one element after the other, go till the end, and when I reach xn followed by empty list, I will replace it by just an empty list, and then I have to put back all the elements that I stripped away. So, xn minus 1, Yeah, so computing init takes number of steps is length of the list. Also for this last, because what do you do for last? You keep on stripping one element after the other till you come to some list of the pattern xn followed by empty list, and you will return that xn. Okay, so this is the definition of last. Last of singleton list x is just x. Last of x colon x's is last of x's. Okay, you don't need to put back the elements, you just need to return the last element, but you have to take time to strip off one element after the other in that list. So that's why it takes time, length of the list, proportional to the length of the list. Okay, so okay, here are some other functions. Take is a function. Suppose I have a list and I want to return all elements from x1 to xn. These are n elements. So I will say take nl. Corresponding to take, there is another function called drop, which will drop nl. So take nl will give me this list. Drop nl will give me the remaining elements. Drop n means drop the first n elements and return the remainder of the list. And actually once again you can actually write this in simple terms. It's a simple recursive function. Let's try to figure out how to write this. Take, let us say, take of 0 of L means I have to return the first 0 elements of the list, which is nothing but just the empty list. Take of n comma n, take n of x colon x's is nothing but x followed by take n minus 1 of x's. This is the basic pattern, but there are some issues. Maybe I asked you to take the first 10 elements of a list, but the list only has 5 elements. So what do you do then? Okay, so these are all cases that one needs to handle. All of these are handled in these definitions. Take, if I want to take any number of elements from the empty list, it is just the empty list, okay, by definition. If I want to take n elements from x colon x's, if n is less than or equal to 0, then I just return the empty list again. Notice that this function is so permissive that I am even allowing negative numbers. Taking minus 5 elements from a list is just saying take 0 elements from a list, okay, extract the first 0 elements of a list. So if n is less than or equal to 0, I again treat it as I treat it like take 0. I return the empty list. Otherwise, I do x followed by take n minus 1 of x's. In the otherwise case, I know for a fact that the list is non-empty, it has at least one element x, and n is greater than 0, so n minus 1 also makes sense. Yeah, so this is the definition. And drop is very similar. Drop any amount of elements from the empty list should give you empty list. Drop n x colon x's. If n is less than or equal to 0, this is like saying omit the first n elements of the list, but you are not specifying any number of elements. You are specifying either 0 or some negative number, which means do not omit anything from the list. So if I say drop n x colon x's and n is less than or equal to 0, the result is just x colon x's. Otherwise, you drop the first element and then you drop n minus 1 further elements from x's. So otherwise, it is just drop n minus 1 of x's. Okay, we will try to program this in the demo session and we will see how this works. but this is it. Note that take and drop are very nice in that take NL plus drop NL, take NL plus drop NL should always return you the list L, no matter what N is and no matter what L is. For all N in integer, let us say positive or negative or 0, for all lists, this equation holds. Okay. So, this is about take and drop. And typically whenever you have a complaint from GHCI or GHCE, whenever you have a warning saying that you cannot apply tail, you can replace tail by drop 1L. It is safer because it won't, it is defined even for the empty list. Drop 1 of empty list is still empty list, whereas tail empty list will give you a runtime error. Maybe you cannot always replace it, you can mostly replace, let me say. Okay, here is another function, and this represents a very nice, a very important aspect of Haskell, of recursive definitions in general. Okay, so this is the function split at NL. I want it to be just this. This should return a pair of lists to me, and the first part of the pair should be the list which consisting of the first n elements of L. The second part of the pair should be the list where which contains everything other than the first n elements. Okay, and of course one could have this definition, but what happens is that in this definition one has to process the list twice. Once for take, once for drop. Okay, so that's a problem. Instead, you might want to directly do give a direct definition, and here is a direct definition. Split at, no matter what it is, if the list is empty, then I know that both take n empty list and drop n empty list is empty. So, I will return the pair empty comma empty. And split at n x colon x's, if n is less than or equal to 0, then I know that take n x colon x's will be empty list, drop n x colon x's will be x colon x's. So, I will just return this. Else, I will compute split at n minus 1 of x's, and then that will be a pair. I can extract the first part, I can extract the second part. The first part is extracted using the function fst. The second part is extracted using the function snd. Recall that fst of AB, the pair AB is A, snd of the pair AB is B. Okay, so I will take the first part of split at n minus 1 x's, second part of split at n minus 1 x's. For the drop part, I don't need to do anything. For the take part, I need to add x to the front of that. So, I do x followed by first of split at n minus 1 x's and then second of split at n minus 1 x's. Let us look at an example. So, suppose I want to do split at 3, 1, 2, 3, 4, 5. Then the first, so n is greater than 0 and the list is of the form x colon x's. So, this will actually be equal to 1 followed by split at first of split at 2 of 2, 3, 4, 5, comma second of split at 2 of now split at 2 of 2, 3, 4, 5 is itself the list. So suppose you have computed split at 2 of 2, 3, 4, 5, and that will be the list. Let's look at split at 2 of 2, 3, 4, 5 now separately. 2 followed by first of split at 1 of 3, 4, 5, comma second of split at 1 of 3, 4, 5, and so on. So you have to recursively compute this, but eventually you will compute split at 2 and then you will return the value. Here it will be first of 2, 3, 4, 5, comma second of 2, 3, 4, 5, and this from here you can actually get to 1, 2, 3, 4, 5. Okay. So this trying to figure out this computation was a little unsatisfactory, because if I actually have to do this, I will have to keep on doing many calls of split at. Note that split at n makes 2 recursive calls to split at n minus 1, even though the argument is the same. Split at n minus 1 will again make 2 recursive calls to split at n minus 2 with the same argument, and in general you do not know whether Haskell will optimize this. So it is possible that your Haskell compiler will take a lot of time to complete this computation, though it is possible also that it does some optimizations, but you are relying on some feature of the compiler. Okay, rather than doing that, here is a better way of doing the same thing. Is this, I will give you cleaner code, and I will also give you code that is much easier to simulate. Okay. So whenever you have 2 recursive calls, multiple recursive calls with the same arguments, then there is a potential that the same computation will repeatedly happen. Haskell will call split at n minus 1 x's once, and after that whole computation is over, later it will come look at the second of split at n minus 1 x's and again make the same recursive call. It's already been computed, why not store it? Okay, but there is no notion of stored variable etc. in Haskell. Rather, I can use local names to bind those names to some values, and I can use those names in my computation. And this I do by using either let or var. Okay, use let or var. Yeah, so actually GHCI has some optimizations to make only one recursive call in this particular case, but you cannot rely on this kind of thing happening all the time. And in general, this is a pattern that you ought to recognize, that if you are doing recursion and you have multiple recursive calls with the same argument, there is potential for wasteful repetition of computation, and it will be very costly indeed sometimes, right? So you have to actually rewrite such things and write better code, and the better code in this case is this. I am using let in this case. So split at whatever empty list is the pair consisting of empty list and empty list. Split at n of x colon x's is, if n is less than or equal to 0, then I return the pair empty list comma x colon x's. Otherwise, you compute split at n minus 1 x's, bind it to the name y's comma z, to the pattern y's comma z, or in other words, use a local definition, give these local names y's and z's to refer to your subcomputation, and then you use y's and z's in your final value, right? So here it is guaranteed that split at n minus 1 is called only once. And now it is also easy to simulate. So let's say split at the same example 3, 1, 2, 3, 4, 5 equals 3 before y's comma z's. That's all you want to do. What is y's and z's? Split at 2 of 2, 3, 4, 5, which is nothing but 2 before, we have to invent some names now, y's prime, let us say, and z's prime. What is y's prime and z's prime? Equals split at 1 of 3, 4, 5. This is nothing but 3 followed by y's double prime, comma z's double prime. What is y's double prime and z's double prime? Is split at 0, 3, 4, 5. No, sorry, 4, 5. But this we know, we have a direct definition for this, which is this. So we will just say that this is nothing but empty list, comma 4, 5. And now we just need to substitute back. Y is double prime, so y is double prime, comma z double prime equals y is prime, comma z primes equals 3 followed by empty list and then 4, 5. Y's comma z's is 2 followed by 3 followed by empty lists, comma 4, 5. And your overall value and your final value that you want to compute is 1 followed by 2 followed by 3 followed by empty list, comma 4, 5. But this is exactly what you want. This is just the list 1, 2, 3 followed by the list 4, 5. Okay. So this is a much better, you can also simulate this computation because in some sense you are making only one call to split at and then you are using that value in 2 places, right. So you are making one call to split at n minus 1, you are naming the 2 parts and you are just using the name of this part here and the name of the second part here in your final expression. Okay. You could also have done it using where you could have said split at n x colon x's equals, if n is less than or equal to 0, then else x colon y is followed by z's, where y is z's is split at n minus 1 x's. Okay. So that is also code you could have written where you use while instead where instead of let. Okay. So that is split at. It's a very useful function. So many a time you will not just want to use take or drop, but you want to split the list at some point. First elements in one part and the remaining elements in another part. Okay, fine. So we even did the simulation. So clearly this takes time proportional to the length of the list, to the length of n actually, because you just make n recursive calls. By the time you reach split at n, split at 0, you will compute some value and start propagating the results back. You could also try split at of the empty list and you will just get empty list, right? Or you could have tried split at 10 2, 4, 6, let's say. Let's see what result we will get. Take 10 of 2, 4, 6 should give you the list 2, 4, 6. Drop 10 of 2, 4, 6 should give you the empty list. So let's see if we split at should therefore give you the pair consisting of the list 2, 4, 6 and the empty list. Let us see how it works. This, so let's call the split at, this thing we will call y is 0, z is 0 is what we want to call it. Is nothing but 2 followed by y is 1 comma z is 1, where y is 1 comma z is 1 is nothing but split at 9 4, 6. But that is nothing but yeah, this is nothing but 4 followed by y is 2 comma z is 2, where y is 2 comma z is 2 is nothing but split at 8, the singleton list 6, and that should be equal to 6 followed by y is 3 comma z is 3, where y is 3 comma z is 3 is nothing but split at 7 of empty list. But at this point we know that split at anything of empty list is just empty list, empty list. So I should get empty list, empty list. So y is 3 is empty list, z is 3 is also empty list, this I get. So I plug the values back in, y is 2, z is 2 should be 6 followed by empty list, comma empty list, y is 1, z is 1 is 4 followed by 6 followed by empty list, comma empty list. That is equal to the list 2, 4, 6 and empty list on the other side. Okay, so this is something we can do. In fact, actually, I needn't even have given the name Z0, Z1, etc. because I am just using the same name here. Zs is just the same Zs. So I could have kept the same constant Zs throughout. Okay, that's fine. So what is the key takeaway here? The takeaway is that local definitions helps avoids repeated computation of the same value.